In this example problem, we have 0.8 meters cubed rigid tank, which contains carbon dioxide at 250 Kelvin and 100 kPa. A 500 watt electric resistance heater is placed in the tank. It's now turned on and kept on for 40 minutes, after which the pressure of the gas reaches 175 kPa. Assuming the surroundings to be at 300 Kelvin and using constant specific heats, determine the final temperature in the tank of the CO2 in the tank, the net amount of heat transfer from the tank to the surroundings, and the entropy generation during this process. Now with this problem, we could draw some assumptions. One, I'm going to assume again that this is constant specific heats. Well, I'm actually going to assume first off that the CO2 is an ideal gas. And then since it's an ideal gas, we need to assume constant or variable specific heats. I'm going to assume constant specific heats. And state 3, I'm going to assume that the change in kinetic and potential energy of the system is 0. All right, so let's go ahead and start the problem. Part A is asking for the final temperature in the tank, which should be pretty direct, pretty straightforward at this point. It would just be an application of the ideal gas law. Using the ideal gas law, I'll go ahead and bring to one side of the equation everything that remains constant, which is mass and volume. And I'll bring the other side everything that's changing, which is pressure and temperature. So with that, I get that P1 over T1 equals P2 over T2. And if I plug in my numbers, I have the pressure at state 2, I have the pressure at state 1, I have the temperature at state 1. I could pretty directly determine that the final temperature would be 437 Kelvin. Part B of the problem is asking for the rate of heat transfer to the environment, which would require a first law analysis. So energy in minus energy out equals the change in energy of the system. As far as what the energy in is concerned, I have electric work in minus the heat leaving the system equals the change in the internal energy of the system. The problem statement is asking me to define Q, so I'm going to go ahead and solve for Q. And the electric work, well, that would be the work rate. So the problem statement tells me that the work rate is 500 watts, so it's 500 watt heater multiplied by the amount of time that the heater is on. So it would be basically 500 watts times 40 minutes worth of seconds minus the change in internal energy, which the change in internal energy for an ideal gas, assuming constant specific heats, would be mCV delta T. So knowing that the work rate is 200 watts, knowing that the time is 40 minutes, knowing that the mass, make sure we're given the mass, we are not given the mass directly, so the mass can be computed using the ideal gas law. Right, so if I'm given that the volume of the tank is 0.8 meters cubed, I'm given that the initial temperature is 250 Kelvin and the initial pressure is 100 kPa. So I can use my ideal gas law, pressure times volume over RT, to figure out the mass. So I can plug that in here. So I have mass, CV I have, T2 I computed in part A, and T1 I can compute that the rate of heat transfer to the surroundings is 990 kilojoules. So again, that's due to a first law analysis. Now again, I don't go through all the numbers, writing in all the numbers for the problem, because at this point, this is something that you guys can do on your own. The point of going through these example problems is just to show you step by step how these problems get worked out. All right, okay, let's go ahead and let's do part C, which is asking for the entropy generation for this process. So part C. So the change in entropy of the system is equal to the entropy transfer to the system by heat and mass minus the entropy leaving the system by heat and mass plus the amount of entropy generated. So we have the change in entropy because there's a state change, therefore there's a change in entropy equals the rate of entropy transfer, right? So there's no mass entering or leaving the system because it's a closed system. So again, no entropy transfer by mass because this is a closed system. But there is entropy transfer out by heat because there's heat leaving the system. So this would be S out. And then we have a rate, and then we have entropy generation. So let's go ahead and calculate the change in entropy. The change in entropy would be that of an ideal gas, so it would be mass times S2 minus S1. It's an ideal gas with constant specific heats. So it'll be mass times Cp natural log T2 over T1 minus R natural log P2 over P1. And then, so if I go ahead and I take this equation and I solve for Sgen, I get Sgen is equal to delta S plus the entropy transfer by heat. So if this is delta S, which is the change in entropy of an ideal gas with constant specific heats, I get Sgen is equal to mass times Cp natural log T2 over T1 minus R natural log P2 over P1 plus the heat transfer to the surroundings, which we calculated according to the first law for part B, divided by the temperature of the surroundings, which was given in the problem statement at 300 K. You plug in all those numbers and you should end up with 3.92 kilojoules per Kelvin worth of entropy generation for this problem.